In the blood of an older person, there's a sugar that should not be there. A fragment made only by bacteria, a molecule younger blood never carries. And your body has a single gene whose entire job is to feel for it. Its name is ALPK1.
ALPK1, alpha kinase 1, sits on the long arm of chromosome 4 at 4q25. It belongs to a strange little family, the alpha kinases, atypical enzymes that don't look like ordinary kinases at all. But ALPK1 is not a housekeeper. It is a sensor, an alarm wired into the inside of your cells. Here is what it listens for. When gram-negative bacteria build their outer coat, they pass through an intermediate sugar called ADP-heptose. Not the finished endotoxin, LPS. That one is caught at the cell surface by a different sensor. ADP-heptose is the unfinished part, and when it leaks into the cytosol, ALPK1 grabs it. That single binding event switches on ALPK1's kinase, and it stamps one phosphate onto a small adapter protein, TIFA, at threonine 9. Phospho-TIFA clumps, copy locks to copy, into a lattice called a TIFAsome, which pulls in TRAF6 and lights up the master inflammatory switch, NF-kappa B. One leaked sugar, and the cell declares an infection. That alarm is supposed to fire and stop. In some people, it doesn't. Change a single letter in ALPK1, threonine 237 to methionine, and the sensor becomes hair trigger. It fires without any bacteria at all. That one dominant mutation causes ROSA syndrome, retinal dystrophy, a swollen optic nerve, an enlarged spleen, no sweating, relentless headaches. A whole body inflamed by a sensor that won't turn off. It is a gain of function, not a broken gene, an overeager one. ALPK1 leaves fingerprints on more ordinary disease too. In some populations, Taiwanese cohorts especially, variants near ALPK1 track with gout, the crystal and fire arthritis. But be careful here. That link is population-specific. It did not replicate in Japanese cohorts, where a neighboring gene carries the signal. ALPK1 is a contributor to inflammation, not its sole author. Now, return to that sugar in old blood. As we age, the gut wall grows leaky, and ADP-heptose, made constantly by our own gram-negative gut bacteria, begins to seep into the circulation. It reaches the blood-forming stem cells in the marrow, where ALPK1 is waiting. The sensor fires, NF-kappa B switches on, and in stem cells that already carry a common age-related mutation, that chronic push hands them an advantage. They expand. This is clonal hematopoiesis, a driver of blood cancer and heart disease, and in 2025, it was traced to a microbial sugar felt by ALPK1, inflammasome made molecular. So, can you drug the sensor itself? For years, the only move was to fight the fire downstream, anti-TNF, anti-interleukin-6, which calms symptoms but doesn't save the retina. Now, there's a sharper tool. A small molecule called DF003 slips into the kinase's ATP socket, the fuel port ALPK1 needs to add its phosphate, and jams it. No phosphate, no TIFA signal, no NF-kappa B. The alarm goes quiet at its source. And because the plug sits in the engine, not the sugar sensor, it silences even the hair trigger ROSA mutant, which fires with no sugar at all. In a first small trial, ROSA patients' inflammation, their spleens, even their sweating improved, then relapsed when the drug stopped, the signature of hitting the real target. And the same axis reaches beyond one rare disease. The scientists who found ADP-heptose in aging blood named this pathway itself, sensor and sugar, as a target to stop those rogue clones before they turn. Whether quieting ALPK1 can bend the long arc of aging, though, no one has answered yet. One gene, feeling for a bacterial sugar, a guardian in infection, a slow arsonist in age. ALPK1, the gene channel.